All right, let's dive in. Today, we're going to take a journey to the very edge of reality, and our guide is none other than the brilliant Stephen Hawking. We're going to try and understand the universe in a nutshell.
So Hawking kicks things off with a huge question. He asks us to think about time like a railroad track. Is it just one straight line always chugging forward? Or, and this is where it gets wild, could it have loops? Could it have branches? Could you go forward and somehow maybe end up right back where you started? It's a simple question, right? But it's one that completely unravels everything we thought we knew about reality.
Okay, so to really get where we are now, we have to look back at how the old picture of the universe just shattered. For hundreds of years, we pictured the cosmos as this perfect, predictable machine, kind of like a giant clock. But then, well, a few cracks started to show up in that perfect facade. You gotta understand, at the end of the 19th century, scientists were so confident. They thought they had it all figured out. They believed space was filled with this invisible stuff they called the ether, and all they had left to do was just measure it. I mean, get this. Harvard built this entire lab with no iron nails to avoid any magnetic interference. The only problem, they totally forgot that the bricks themselves were packed with iron. And it's hilarious, right? But it shows you just how certain they were. And then, bam! The first massive crack in that old worldview. And it came from Albert Einstein. He completely flipped our understanding of gravity on its head. He showed that it's not some mysterious force pulling things together. Nope. Instead, massive objects, things with a lot of energy, literally bend and warp the very fabric of space-time. Think of it like dropping a bowling ball onto a trampoline. That's what planets and stars are doing to space and time itself. The next big crack came from just looking up at the sky. It started in 1912. An astronomer named Vesto Slipher noticed that the light from these distant, fuzzy patches, these nebulae, was redshifted. Basically, the light waves were stretched out, which could only mean one thing. Those objects were moving away from us, fast. Then, fast forward to the 1920s, and Edwin Hubble has this mind-blowing realization. Those aren't just little gas clouds in our galaxy, they're entire galaxies, millions of light years away. By 1929, the conclusion was inescapable. The universe wasn't just sitting there, it was expanding. Everything was rushing away from everything else. So while Einstein is busy rewriting the rules for the really big stuff, stars, galaxies, the cosmos, a whole other revolution is kicking off. Physicists started diving into the world of the super small, and what they found was that the universe's tiniest building blocks, well, they play by a completely different and, frankly, much weirder set of rules. And you know who hated this new quantum theory? Einstein, the guy who just upended all of physics. He was absolutely horrified by it. He just couldn't stomach the idea of a universe where the most fundamental laws were based on pure chance and probability. That's where his famous line comes from. God does not play dice.
So what was at the very heart of his problem with it? A little thing called the uncertainty principle. It's a simple idea, but it's profound. It says you can know exactly where a particle is, or you can know exactly how fast it's going, but you can never, and I mean ever, know both of those things at the same time with perfect accuracy. And this isn't because our tools aren't good enough. No, it means randomness is literally baked into the fabric of reality itself.
But then, you've got Stephen Hawking who comes back with this brilliant, witty counter. He said, all the evidence is that God is quite a gambler. He saw the universe as this giant casino. You can't predict the outcome of a single roll of the dice, right? But if you roll them millions and millions of times, the laws of probability kick in. And in the end, the house, the laws of physics, always wins. And this quantum weirdness, it just keeps going. Think about a pendulum. You'd think that at its absolute lowest energy state, it would be perfectly still, right? Wrong. It can't be. Because if it was perfectly still, you'd know its precise position and its precise speed, which would be 0. And that would violate the uncertainty principle. So what does that mean? It means that even in a perfect vacuum, empty space isn't really empty. There's this constant, underlying fizz of quantum fluctuations. Wow. Okay, so let's recap. We've got two completely new sets of rules for the universe. One for the very big, relativity, and one for the very small, quantum mechanics. And when you start pushing these incredible new theories to their absolute limits, well, you start getting some truly mind-bending results. Let's imagine a really massive star. I'm talking more than 20 times the mass of our own sun. Eventually, it runs out of fuel. And when that happens, gravity just takes over. It wins. The star collapses under its own immense weight,
and it warps space-time so violently that it literally punches a hole through reality. At its center, you get a singularity, a point of infinite density, and around it, an event horizon that nothing, not even light, can escape from. You've just created a black hole.
So, if space-time can be warped and bent that much, could it break? Does this crack open the door to the ultimate science fiction fantasy? Could we actually find one of those branches in the railroad track of time? Could we travel to the past?
And listen, these aren't just questions for sci-fi conventions. The top physicists in the world were debating this stuff. Guys like Hawking, Kip Thorne, and John Preskill made actual, real-life bets on the nature of reality. This one from 1997 was about whether something called a naked singularity could exist, basically a tear in space-time that isn't hidden inside a black hole. And the stakes? The loser had to buy the winner some clothes to cover the winner's nakedness. You gotta love physicists.
All of this, it leads us to the holy grail of modern physics, the ultimate quest, the search for one single, elegant theory that can finally bring those two great pillars, relativity and quantum mechanics, together. A theory that could explain, well, everything.
And here's the fundamental problem, the big conflict. You've got general relativity on one side describing this smooth, predictable, curved space-time for big things like stars and galaxies. Then, on the other side, you have quantum mechanics, describing this jittery, random, probabilistic world for tiny things like atoms and particles. The two theories are brilliant on their own turf, but they just don't play nice together. The math for one completely falls apart when you try to apply it to the other, especially in extreme places, like inside a black hole or at the moment of the Big Bang.
So how do we find the clues to bridge that gap? Well, we build these absolutely colossal machines, things like the Large Hadron Collider in Geneva. What do we do there? We smash tiny particles together at almost the speed of light over and over, hoping that in the debris of those collisions, we might catch a glimpse of the deeper underlying laws that govern the whole show.
Right now, the best candidate we have for this theory of everything is something called M-theory, and it's a wild one. It suggests that our universe doesn't have 4 dimensions, but 11. Yeah, 11. We only experience 3 dimensions of space, plus 1 of time, right? So where are the others? M-theory says they're curled up incredibly tightly, so small that we can't see them. The analogy Hawking uses is a garden hose. From far away, it just looks like a one-dimensional line, but if you're an ant on it, you know it has a second, circular dimension. That's what the other dimensions of our universe might be like. It's our best shot so far at a single theory for all of reality.
And if M-theory, or some other theory like it, turns out to be right, just think about what that means. It would give us a complete, self-contained description of the entire cosmos. A universe that doesn't need a creator, that doesn't need any cause from outside itself to get started. In Hawking's own words, that is the universe in a nutshell.
So after this incredible journey through space-time and quantum weirdness, Hawking brings it all right back home, back to us. With everything we're learning about the universe, what does it all mean for the future of humanity? Where are we actually headed?
Just look at this comparison. It's kind of staggering. Our own DNA, the very code of life, evolves at a snail's pace. Hawking figured it changes by about 1 bit of information per year. 1 bit! Meanwhile, our technology is just exploding. You've probably heard of Moore's Law. It says that computer complexity doubles roughly every 18 months. That gap between our biological evolution and our technological evolution is getting wider and wider incredibly fast.
It's actually pretty humbling when you think about it. Right now, our most powerful supercomputers are still less complex than the brain of a simple earthworm. Yeah, an earthworm. But given the absolutely blistering pace of Moore's Law, you know that's not going to be true for very much longer.
And this is what leads Hawking to his most startling and maybe controversial conclusion. He argues that for us, for biological life, to have any hope of keeping up with artificial electronic intelligence, we can't just wait around for natural selection to do its thing. It's too slow. He predicts that the human race will have to take control of its own evolution. We'll have to start redesigning our own DNA through genetic engineering. And that's why Hawking just didn't buy into futures like you see in Star Trek, where humans 400 years from now are pretty much the same as us. He was convinced that fundamental change is coming. So the question he really leaves us with is a big one. As we continue to unlock the deepest secrets of the cosmos, what kind of future are we going to choose to build for ourselves?